Greetings, everybody. So the topic of today's video, which is actually from the PACET conference on 2024, has to do with studying a chaos-based random bit generator using different chaotic maps. So let's begin by talking a little bit about our applications. I mean, we are mainly interested in chaos-based symmetric encryption. And this means that on our transmitter, we are using some sort of information signal, and we use a chaotic system in order to encrypt it, usually discrete time map. So then we can safely transmit this signal through a public channel. And then at the receiver end, the receiver is using the exact same chaotic signal, using the exact same chaotic keys, for example, the same initial conditions and the same parameter values, in order to reverse the encryption process and obtain the information signal back. Okay, so this is why it's called symmetric encryption. Okay, and of course, relevant to symmetric encryption, we have other applications, related to security. For example, we have chaotic password generator. We can have chaotic path planning for autonomous robots or chaotic surveillance. There's a plethora of applications related to security that utilize chaotic systems. So all of these applications, what do they have in common? What they have in common is that all of them use chaotic random bit generators. Okay. So the idea here is this. We can input some specific keys or secret keys to our chaotic system, parameter values and initial conditions. This chaotic system then generates a chaotic time series. And then we take this time series and apply some sort of hash function, so some sort of nonlinear function, in order to generate some random bits. Okay. So this is very basic. I mean, it's very fundamental in any application related to chaos-based security in general. And here we have a set of specific goals. Okay. So let's talk about them. First of all, we want to achieve a high key space. Okay, this has to do with being able to resist brute force attacks. So our first goal is this. Secondly, uh, our chaotic system and our hash function need to be relatively lightweight. So they cannot be extremely time consuming. Okay. Of course, they need to be fast, but they also need to be secure and efficient. So ideally, the hash function should be such that hides the relation between the chaotic system and the output bits. Okay, so this transition from the time series to the bits could not be reversible. So this hash function should be somewhat non-linear and somewhat complex enough, right? Of course, additionally to being lightweight to some extent. And of course, after we do all of that to get our bits, obviously we want a random bit generator. So the bits should be statistically random, right? So we need to test that as well. So these are the basic goals when designing a chaotic random bit generator. Ideally, you want to have all of them being satisfied. So at the moment in the literature, I mean, there are many, many different chaotic maps, right? And there are many, many different PRBGs. Of course, all of the bit generators pretty much use a collection of standardized techniques to generate bits, right? So there are similarities. But each of these papers, like, each paper uses their own chaotic map. They test the map, but they don't test any other maps in this PRBG. So here we have a very natural question rising. Okay, we have so many PRBGs that are pretty much the same. We have so many different maps, but I mean, can we interchange them? I mean, how can we say that we have a PRBG that it's like universally working well? So this is an open question because, uh, each paper uses their own map. So we need to test, and that's our motivation behind this work, that uh, when we have a specific basic, as we say, if we can say this basic PRBG, how does it, behave compared to different chaotic maps used? So that's what we studied here. We started by taking a very standardized random bit generator. We used some classic techniques like the modulo and the binary conversion. Let me tell you how it works. We multiply the time series by a very large number. Okay. So after we obtain a very large number, we take this modulo 256. So we obtain an integer from 0 to 255, and then we transform it to a binary value. So this bit generator gives us 8 bits per iteration of the map because we do the conversion of decimal to binary, right? So this classic PRBG we tested it on 10 different chaotic maps. And we took many different maps from the literature, like the logistic and the sign map, which are very, very classic. But we also took some maps that are more recent for like publications from the last couple of years, right? And we tested all of them with respect to all the conditions that I mentioned earlier. So first of all, let me talk about the PRBG. It is very standard, as I said, but it also has a very good characteristic regarding the balance between the number of operations and the number of bits produced. Because we have 4 operations overall and 8 bits produced. Okay, so the ratio between operations and bits is 4 over 8, so like 50%, which is a very good balance, right? So first thing we checked, of course, is statistical randomness. Because if you don't have a random PRBG, you cannot use it. Okay, so what we found out is that for the 10 maps that we used, that are, have very varying forms with each other, 5 of these maps pass the statistical tests. Okay, so as you see right here, some of them are very classic, like the RENWI map. The others are all more recent maps. Okay, so already we have a good result. We have 5 maps that are statistically random with this PRBG. So any reader here can use them for their own applications. Then we tested key space. So all of these maps have a high key space. Traditionally we say that the key space should be larger than 2 to the 100th to resist brute force. All of them are higher. Some of them, of course, are only slightly, like the RENWI map, but the other 3 that I have right here are much, much higher than the threshold. Okay. So again, good characteristic. We have high enough key space for all of our maps, right? And then we combined the PRBG with a map to measure the ratio between operations and the bit output in combination of the PRBG and the map as well. Okay, so for all of these 5 maps, we have relatively good ratio. The RENWI map, which is a classic one, has a very good ratio. It's 75% between operations and bit output. But the other ones are also good. They are only slightly higher than 1. So all of them have a very good ratio between the number of operations required and the bit output. Okay. Of course, I should mention here all of these operations like addition, multiplication, trigonometric, they don't have the same complexity. So if you want to actually measure the speed of the PRBG, especially in microcontrollers, you need some testing and experimentation. But as a theoretical value, this is a very good result. Okay. So overall, what we have? Okay. We have PRBG with 5 chaotic maps that is already suitable for use. So any of you want to do like chaos-based encryption, security, optimization, or whatever, you can use directly the PRBG that I have for these specific 5 maps. Okay, they are resistant to brute force attacks. They have a good balance. So they are ready for use. Okay. Another thing we noticed is that for all the maps we tested, it seems like, when you have modular nonlinearities or sign exponential nonlinearities, they are generally able to give a better mixing. So, they generate more complex time series. So these maps seem to be more suitable in passing statistical tests. And of course, another note that we have here is, remember, we need to keep the design as lightweight as possible. So ideally, if you use more secure maps that are, more complex and they have like higher nonlinearities like the modulo, ideally the map will become more complex, the time series will be more complex. So ideally you can use a hash function as a post-processing tool that is going to be a bit lighter. So you don't need a lot of operations in the hash function in order to generate random bits. So, the better maps will generally improve the design overall. So this is another good result that we have in our analysis. Okay. So in the future, I mean, we want to continue researching PRBGs. What we have in mind is possibly test more maps. I mean, we have already tested a lot. I mean, 10 maps are a lot, but maybe going to like analyze a little bit further, maybe going to 20 or 25 chaotic maps from the literature. Maybe in combination with some students, we want to do a microcontroller implementation in Arduino boards or whatever and measure the speed between each different chaotic map and the bit generator. And ideally, what I have in mind is doing a web page implementation. So we want to implement the PRBG on a web page, on a web interface. So, anyone can visit this page, input their keys, and for example, they get as an output a TXT file with as many bits as they like, in case they want to do experimentation, optimization, encryption, or whatever. So we can generate our bits on the web, and you can download it yourself as you like. So these are pretty much what we have as goals in the future. So more importantly, in the description of this video, I'm going to put the link to the paper so you can download and read it. And also I'm going to put a link to MATLAB file exchange where I have the code that you can use in MATLAB to implement the PRBG yourselves. Okay, so you can use it with any map that you like and apply it to any application that you like. Okay, so this is it for today. Thank you very much.